This is Physics 1060, Descriptive Astronomy, Lecture 3, and today we're going to start going over Chapter 3. We'll start by looking at some historical astronomy, specifically the size and shape of the Earth. Until the 16th century, all astronomy was done with just your naked eye, just looking up into the sky. But you can do a lot of astronomy by just looking. For example, the Greeks knew that the Earth was round because the shadows of lunar eclipses were round. The only way that an object can always cast a round shadow is if it itself is spherical shaped. So by studying shadows and eclipses, the Greeks actually worked out pretty reasonable values for the sizes of the Earth and the Moon and how far apart they are. They didn't know the distance to the Sun, except it was a lot further away than the Moon. It's really a fallacy that the Greeks or the early Europeans, like Christopher Columbus, thought that the Earth was flat. Anyone who had had any education at the time knew that the Earth was round. The things the Greeks got wrong, though, was that they put the Earth at the center of the solar system instead of the Sun. And this is called a geocentric universe. There were some Greeks who did get it right, but Aristotle was wrong, and Aristotle's views were given as much weight as the Bible for thousands of years. Now, this dispute between geocentric and heliocentric, which means sun-centered, theories, is one of the most important events in the history of Western civilization. The acceptance of the heliocentric theory led directly to the rise of physics and the scientific way of looking at the world. No modern technology would exist today if the heliocentric theory had not won the day. The dispute was not just about whether the Earth goes around the Sun or the Sun goes around the Earth. The key difference is whether everything else goes around the Earth or around the Sun. In a geocentric universe, the Earth is at the center of the solar system, and the Moon and Mercury and Venus and the Sun, all the planets go around the Earth. Now, the rise of the heliocentric theory came about by a series of ideas and discoveries that illustrate the different styles of scientific work. One of the things we will learn is a common feature of science. When we try to solve one particular problem, and the end result turns out to explain all sorts of things that are not directly related to the original problem. So if I'm studying one thing, I discover other things. It's one of the reasons that, for example, the U.S. government puts a lot of money into basic research. A lot of research topics, different people might say, why are we doing that? Why? I don't see the application for this. I don't see how this is going to help. It's because we know that studying one thing often leads to big discoveries in other areas. So, the planets. The word planet is from the Greek word wanderers. So the ancients knew of 5 wandering stars, or 5 planets, plus the Sun and the Moon: Mercury, Venus, Mars, Jupiter, and Saturn. They didn't consider the Earth a planet at this time. Now, of course, since the invention of telescopes, we've also had Uranus, Neptune, and Pluto. So, Pluto. We'll talk more about Pluto later. The International Astronomical Society demoted it in 2007. I kind of still think of it as a planet just because of the era I grew up in. But we'll come and talk more about Pluto in a minute. So the planets rise and set with the daily rotation of the Earth. But their positions compared to the background stars change slowly from week to week as they orbit the Sun at different speeds. Now, the planets are going to move roughly, but not exactly, along the ecliptic. Remember, that's the path that the Sun takes. So as I watch Mars go across the background stars here, we see that it goes and moves very slowly against the stars over a course of several days. But then every once in a while, it's going to turn around and go backwards. It's this backwards motion that it's called retrograde motion that we're trying to understand, or the early astronomers were trying to understand. Now, as we continue to watch, we'll see the Sun come into view. Since this is the ecliptic, it's the path the Sun goes around the sky. We might even see some other planets. We see the Moon flipping by every once in a while. So here comes the Sun, and we see here some small other planets. Like here's Venus as it moves across, it's going to go around the sun, or maybe that's Mercury. And then it does retrograde also. It's going to slow down. No, maybe it didn't. Here's another little planet that's doing that. Anyways, all the planets have the same retrograde motion. They'll move in the same direction for quite some time, and then every once in a while will stop, turn around, and move a different direction. So when looking at it, Mercury and Venus move side to side about the Sun. Mercury gets about 28 degrees, Venus about 47 degrees away from the Sun at any time. And Jupiter, Mars, and Saturn move along the ecliptic, and they make that retrograde or reverse motion every once in a while. The crucial point is to explain the motion so we can predict the future planet positions of the planets. Now this was really important to some of the very earliest people because they needed to know, for example, when to plant. Because, you know, sometimes in February, especially in Idaho, it'll start to warm up and you might think, oh, it's time to plant my plants. But then you'll get this late frost in the end of March, early April, and you lose all your food. Or maybe you were people that needed to follow the motions of the migratory herds. And so if you took your people too early or too late to certain areas, there wouldn't be any food there and you'd starve. So it really was important to lots of different civilizations to understand the motions of the stars and planets. So early civilizations observed the regular motions of all the heavenly bodies, which the planets they called gods, and gave names to groupings of stars, the constellations, some of which we still use. They made those observations again because they needed to know the seasons for planting harvests, for when to find the migratory herds, or maybe even for religious celebrations. And so their observations of the regular motions of the planets, moon, and sun and stars led to the first attempts to make a calendar. The Egyptians are credited with the first discovery of a 365-day year and a 30-day month. Now, all the calendar attempts were less than accurate because there's really 365.24 days a year and 29.5 days per month. And the early people couldn't detect this slight difference, so their calendars got off every once in a while. A Stonehenge, for example, is an ancient astronomical device for telling time. So the ancients discovered the 5 visible wandering stars or planets. And a lot of them thought them to be gods and linked constellations and planetary motions to fortune or misfortune, a belief termed astrology. And they named and identified the zodiac, the belt of constellations along the ecliptic, or the path that the sun goes around the earth. The Babylonians produced constellation maps, and very accurate calendars have been found in caves along the Euphrates rivers. And there's lots of other these great astronomical devices for telling the time of year, like Stonehenge, which I showed, or this picture here is the bighorn medicine wheel. It was a rancher who found these rocks in this pattern on his land at one point in time, went and asked somebody about them and found out it was an ancient Indian time or of the year telling device. Of course, the Anasazi buildings in New Mexico have lots of these sort of devices, and we'll see some of them and a little more explained in the video on Kepler that you're going to watch a little bit later. So Greeks, Pythagoras, maybe you remember him from the Pythagorean theorem in high school, but he was one of the first astronomers to propose a geocentric system of the Earth, Sun, and stars. Eudoxus taught that the stars existed on a huge sphere which rotated around the Earth each day. Aristarchus countered this theory, proposed that the spheres of the planets, suns, stars, and moons stood still and the Earth rotated on its axis once per day. He also suggested a heliocentric system, but he was rejected by all the scholars of his day. Hipparchus kept records and positions of 1,000 stars and used his star chart to plot the motions of the planets very accurately. But he could never say why they moved the way they are. Finally, of course, we get to Aristotle, who was a great thinker and philosopher held in very high respect. and he proposed 55 different concentric crystal spheres around the Earth, which the sun, the planets, and the moon and stars all existed. Of course, he taught that everything we see was composed of some combination of the 4 prime materia: fire, water, earth, and air. He made very careful records of the retrograde motions of the planets against the background stars, but could never explain it. However, his influence was so powerful that the idea of a geocentric system remained for 1800 years. So next Greek we want to talk about is Ptolemy. He lived about AD 140, and Ptolemy developed a very sophisticated geocentric theory. The basic thing he was trying to explain is why the planets move so evenly along the ecliptic. And the basis of his theory was what we call a scientific model. He had some strange things. He had circular orbits with epicycles. There's nothing at the center of an epicycle. I'll show you what one of those is in a second. So one has to think of planets making circles around an empty point in space that's making a circle around the Earth. Circles were really intellectually satisfying to Greeks, so they assumed that nature was based on circles. Greeks really liked all the perfect shapes, so regular solids and circles. It appealed to them in how simplistic in nature was, and so they really tried to base a lot of what they were looking at in the universe on these perfect shapes. So if we look at Ptolemy's universe, we have Earth in the center, and the moon goes around the Earth. Mercury and Venus, the center of their epicycles, are tied on the line between the sun and the Earth. So they move on a circle, but it's tied, so they're always close to the sun. The sun, of course, goes around the Earth, and then the rest, like Mars, as the center of its epicycle moves around, it goes around in loops on this epicycle. So here we are. This circle around the Earth is not necessarily in the center, is called a deferent, and there's a point on it, imaginary point on the deferent that the epicycle is connected to. So as the planet goes around, it every once in a while goes backwards and forwards as it appears from the Earth. So in Ptolemy's model then, if we were to follow it, see how Mars, as it appears from the Earth, appears to go backwards just because the line of sight from the Earth to Mars is changing as it goes backwards on this epicycle. So Ptolemy's theory gave very nearly the right answers, and his equations and tables were used for over 1,000 years to predict the positions of planets. And he was held in such high respect that when it wasn't right, when something went wrong, the sky, something happened out there, that was what went wrong. Then they used his model to recalculate all the tables to figure out when Mars and the other planets would go into retrograde motion. So now if we look how the Ptolemaic universe looks like, here we have Earth in the very center, and as we let it go, we notice all the planets go around. They appear to go backwards and forwards around. It's a very complicated thing. It worked. It worked for predicting where the planets would be at any point in time. However, it's not very pretty. Now along comes Copernicus, and he's really recognized as the driving force behind the acceptance of a heliocentric or sun-centered theory, although we saw at least one Greek philosopher had the idea first. It's a Polish astronomer, and his theory was disliked by authorities mostly because it relegated Earth to a position of no more than a planet. Earth was no longer the center of everything. The change from the geocentric to the heliocentric view of the universe is so important we refer to it as the Copernican revolution. So now if we look at a Copernican universe, the sun is at the center of everything, and as we let that go, we see that everything forms these nice circles around the sun. This is a much more elegant, because the Earth is moving, it provides a natural reason why the planets go backwards and forwards, just as Earth and Mars move at different speeds as they're going around the sun. And so it's a lot more elegant. So the Copernican picture is much simpler conceptually. Planets no longer go around nothing, they go around the sun. The Earth behaves in much the same way as any other planets. It's a much simpler model, and simplicity is the main reason for its acceptance. This is an example of one of these great guiding principles of science called Occam's razor. Roughly it says, if you have two theories that fit the observations, the simpler theory is almost always the one that is going to be correct. Copernicus's model had a natural explanation for the fact that Mercury and Venus are always close to the Sun, because they're going around the Sun closer than the Earth, and for things like the retrograde motion of Mars and Jupiter and Saturn. The problem is the theory is still based on perfect circles. He was still influenced by this Greek thought, and because of that did not make any better predictions than Ptolemy's theory. So now I have two theories, one that's been handed down from the ancients who knew more than we did, one that's simpler. Which one do we choose? This is the basis of the Copernican revolution. Not necessarily whether one model or another is correct, but how we view the world around us. Do we take what we see or what we've been handed down information, or do we take what we can reason out as more correct? So here's kind of the crux of things, and it's really going to come to a head when we get to Galileo. Now the next person we need to talk about is Tycho Brahe. He's a Danish nobleman. He had a false nose. When we watch the Kepler video, you'll see a little bit more about that. Essentially, he got in a fight with another mathematician over who was the better mathematician. Swords were drawn. He lost his nose. He was a superb experimentalist. He had great data without a telescope. He had this observatory, and in the observatory was a large quadrant. And here's a picture of him directing everything. Here's a person that's looking through. What they had is a slit in the ceiling that went right along the meridian, and they could tell when an object passed the slit. And inside this movable telescope here were two hairs that were crossed, so you knew instantly and at what angle, so therefore what height in the sky, something crossed the meridian. This guy down here would record the time, and this person would record all the data in a book. So we get angle measurements of planets with respect to stars, timings when stars cross the meridian. Tycho did not support Copernicus, but that didn't diminish him as a great collector of data. That brings us to Kepler. Kepler worked with Tycho Brahe, as you'll see in the video of Kepler's life. Eventually he inherited and analyzed Tycho's observations, and he tried to look for patterns. He had several false starts. He concentrated on trying to find a model to fit the observations of Mars. It took him 20 years of crunching the numbers, essentially, discovered that the crucial point was that planets move in ellipses about the Sun, not circles. So Kepler came up with 3 laws of motion that describe the motion of the planets. You need to understand these laws. The first, Law 1, is the orbit of a planet around the Sun is an ellipse with the Sun at one focus. Now remember that a circle is a special case of ellipse, where the two focal points come together in the center. The focal point is a special point on the ellipse. Remember to draw an ellipse. If you remember from high school, you take 2 points, you take a string, and the distance between these 2 points and the edge of the ellipse is always constant, and you can make your pencil go around, keeping the string tight, and form an ellipse. The line that goes through the focal points to the edges of the ellipse is called the major axis. If you go from the center to one side, that's called the semi-major axis. So planets move in this elliptical orbit with the Sun at one of these focal points. His second law says a line joining the planet and the Sun sweeps out equal areas in equal intervals of time. It's really a law about the speeds in an orbit. So for example, if I were to take this imaginary line between the Sun and the Earth, and I were to follow it and how much area it sweeps out in, let's say, a month of time, the area it sweeps out here and the area it sweeps out here are exactly the same. The areas of A, B, and C are the same. That means that at sea it has to be moving faster here than it is here. And Law 3 states the squares of the periods of the planets are proportional to the cubes of the semi-major axes. Period squared is equal to some constant times the cube of the distance it is away from the Sun. P is the period, just means the time it takes the planet to make one orbit around the Sun. K is just some constant. In this case, it's going to include the mass of the Sun. And A is the semi-major axis of the ellipse. Since most planets are nearly circular, we can approximate A as the radius of the circle. And so the third law connects the periods of the different planets as they move around the Sun. Usually, we don't need to specify a specific value of K. If we compare periods and sizes of two planets, the K's cancel out. You just get an equation like this. All three laws can be applied to other orbiting systems, such as the moons of Jupiter. And note that the actual value of K would be different for objects orbiting the Sun or orbiting Jupiter. For the Sun, if we measure the period in years and A in astronomical units, and one astronomical unit is the distance from the Sun to the Earth, then K is equal to 1 and it becomes simple. Now, Kepler offered no explanation of why these laws hold. The strength of his theory is it allows much more precise prediction of the positions of the planets than Ptolemy's theory. So his three laws are much simpler than the complicated ones of Ptolemy. And remember, in science, simplicity is one of the most important aspects to any theory. Now, this didn't prove that Copernicus was right. It was just a better theory. Again, we're still, at this point in time, struggling between information handed down by the ancients versus observations that we make. We're trying to find out, as a people, which is the better method for determining science. Now, eventually we get to Galileo Galilei. He's an Italian astronomer. And Galileo's genius was he was the first person to use a telescope for astronomy. Telescopes had been around for a little while when he started. But they were used for maybe a ship captain looking to see if there's something out on the horizon, or someone at one location trying to see something far away on a hill far away. No one had ever actually tipped the telescope up and looked at the sky. Now, Galileo's notebooks still survive, still provide important details for people who need to know how the sky looked in the 16th century. So Galileo made a lot of studies, craters of the moon, sunspot, stars in the Milky Way. There were 4 particularly interesting observations he made that pertain to the heliocentric controversy. His first discovery was the moons of Jupiter. Seen here, this is the Earth's moon for a size comparison. We have Io, Europa, Ganymede, and Callisto. So he discovered these 4 large moons, and really they're only just too faint to be seen with the naked eye. If you have just a simple pair of binoculars and look up at Jupiter, you'll be able to see the 4 moons of Jupiter. However, the philosophical importance of these observations is it shows not everything orbits the Earth. Galileo, over the course of a night, was able to see the moons come out from behind Jupiter, go around Jupiter, and disappear behind it. And the moons obeyed Kepler's laws themselves. So here we have a first chip at this Ptolemaic and this ancient Greek theory that everything revolves around the Earth. So maybe they said, all right, maybe everything doesn't revolve around the Earth, but the Earth is still the center of the universe. We maybe can change Ptolemaic theory a lot, but it's still the Earth is at the center. So the picture here is Galileo's observations of Jupiter's moons. You can see over the course of a night he saw them change. They were most recently observed by a NASA spacecraft named after him called Galileo. Discovery number 2, that there are mountains on Earth's moon. He observed the moon with his telescope and noticed that there are shadows of the mountains on the moon. The moon could be the perfect crystal sphere imagined by Ptolemy. All these objects in the sky were imagined to be perfect crystal, perfectly smooth. The colorations would be like the colorations of marble. You can be smooth but still see the colors. But Galileo looked and actually saw that as the phases of the moon changed, the shadows on the moon changed. So again, this chips away at Ptolemaic theory. Proponents said, all right, maybe the moon is rough, but still the Earth is at the center of the universe. By the way, those of you who are in lab, we're actually going to measure the height of some mountains on the moon using Galileo's method, just by observing the shadows on the moon. Discovery number 3 was sunspots. Sunspots, as we're going to see, are small dark regions on the surface of the sun. They revolve around the sun on the surface of the sun, and they change shapes. And they could be large. This picture here, we could fit 3 or 4 Earths in this sunspot itself. Now, this is another proof that the celestial objects are not perfect spheres imagined by Ptolemy. In fact, it's even worse than that. It's not that it's not a perfect sphere, it's not even a solid. Because if we look at the sun, we notice that sunspots move around the sun every 25 days at the equator and every 35 days at the poles. So the only way that I can have different rotational periods at different places on an object is if it's not a solid, it has to be a liquid. Discovery number 4 was the phases of Venus. So if I look at Venus, this picture here is Venus seen through a telescope, same magnification. We notice it gets very small and very large, and Galileo could see changes in the apparent shape of Venus due to the changes in the way it's illuminated. This is a crucial confirmation of the Copernican theory, since it proves that Venus goes behind the sun. Now, if we look at a Ptolemaic universe, remember, the center of the Venus epicycle is on this line between the Earth and the Sun. And so Venus goes around as the Sun goes around the Earth. Now, if I look at this carefully, I notice that Venus then is always between the Earth and the Sun. The backside of Venus would always be lit. You would never get a full phase of Venus. All you would ever see is a crescent phase. However, in a Copernican universe, since Venus goes around the Sun, there will be times when it's on the far side of the Sun where it would be in full phase. When it's on the near side, it would be a crescent phase. There is no way the phases of Venus can be explained using Ptolemy's model. This was kind of the nail in the coffin for Ptolemaic theory. It proved it had to be true. There's no way that we can hold on to anymore this geocentric theory of the universe. Now, Galileo also made important experiments in mechanics. He showed that heavy and light things always fall at the same rate. He introduced the ideas of acceleration and realized friction was what slowed things down. And acceleration is just the rate of change of speed or velocity. Galileo didn't ever try to connect his astronomy with his mechanics experiments. And it's going to take the next scientist we'll talk about, to Newton, to put this all together. So Isaac Newton is generally regarded as one of the greatest physicists ever. He wrote a book on optics and mechanics, which is the science of how things moved. He invented calculus to explain the things that he was trying to do in mechanics. And he knew all about Galileo and Kepler's discoveries. And he wanted to understand what are the underlying physical laws that could make sense of the patterns his predecessors have discovered. Why, for example, should planets move in ellipses rather than some other shape, maybe a figure 8 or a square? What causes them to move in that particular shape? This is the scientific question. Why does something behave the way it does? Newton is also responsible for unifying the laws that explain the behavior of planets and the things on Earth. And today, scientists take it for granted that the laws of nature are basically the same everywhere. But before Newton's time, there was no reason to assume that things that happened up in the sky, up in the heavens, behaved in the same way as things did on Earth. Now, the most fundamental of Newton's laws are his 3 laws of motion. And in getting these, Newton built on the work of Galileo. The 3 laws apply to any matter, not just planets, and they deal with the way motions are related to forces. So Newton's first law, and you should have these memorized, states that a body remains at rest or moves in a straight line at a constant speed unless acted on by an outside force. So before Newton, it had been widely held that objects had a natural tendency to stop moving, and he recognized there was this role of friction in stopping things, and realized that friction itself is a force. If you take away friction, like in space for example, things keep moving indefinitely. Another consequence of Newton's first law is that you need a force to change the direction of motion, such as going around a bend or around an orbit. Law 2 states the acceleration of an object is proportional to the force acting on the object. It's the most mathematical of the laws, and it's sometimes written as force is equal to mass times acceleration, or F equals ma. So the force here could be a push, it could be gravity, it could be magnetism, air pressure, friction, whatever. An acceleration is the rate of change of velocity. And for physicists, braking is a form of negative acceleration. The mass of a body is the amount of matter it contains. Loosely speaking, it's similar to a body's weight. Mass is not the same as volume, which is essentially the size of an object. So for example, if I have a handful of shaving cream, as it expands, the mass stays the same, but the volume may increase. The length between mass and volume is density. Density is mass over volume. So things like iron have a high density, air has a low density. And the other thing that F equals ma implies is that acceleration is in the same direction as force. Now this equation looks simple, but as any of my physics students soon find out, mechanics gets very complicated when a single object is acted on by several forces, or when we have to consider a complicated object made out of many small ones. Newton's laws show us how very complicated motions are actually the result of simple interplays between force and mass. This is called the analytical aspect of science. Law 3 states that whenever one body exerts a force on a second body, the second body exerts an equal and opposite force on the first body. You've often heard this as for every action, there's an equal and opposite reaction. So, if I shoot a gun, the recoil of the gun is an example. There's a force pushing the bullet one direction, and the bullet pushes back on the gun the other direction. Or if I jump off a skateboard, as I jump off, I'll go one direction, and the skateboard will go on the other direction. Now, the other great law that Newton came up with is not called the fourth law because it deals with one particular kind of force. The first 3 laws are completely general and deal with all kinds of forces. So his next law that he is known for is called the law of gravity. 2 bodies attract each other with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them, where F is g, where g is called Newton's gravitational constant. We just look it up. Mass of one object, mass of the second object, divided by the distance between them squared. So before Newton, gravity was a force produced by the Earth and nothing else. But when Newton thought about the implication of his first 3 laws, he noticed that since the Earth's gravity makes objects accelerate, gravity must be a force like any other. Thus, as the story goes, as he's watching an apple fall under the apple tree, it fell to the earth because the earth exerted a force on the apple. But if he believes his third law, if the earth pulls on the apple must also pull on the earth. So Newton's genius was to realize that if the apple could pull the earth, it could probably pull anything else as well. So he hypothesized that all matter attracts all other matter. Now, Newton's law of gravity is an inverse square law, which just means the force is proportional to the 1 over the square of the distance between them. So it shows that gravity gets weaker as things move apart, which is opposite as, say, the force of a piece of elastic, which gets stronger as it's stretched. If you take a rubber band, it's very easy to stretch it at first, and it gets harder and harder. So the force between two objects can be measured in the lab, but it's difficult because the force between these two small bodies is very weak. That letter G, I said, is the universal constant of gravitation. We look it up. As far as we know, it's the same everywhere in the universe. So one of the greatest successes of Newton's law of gravity, coupled with his other laws, is that it explained how orbits work, both qualitatively and quantitatively. So in Newtonian physics, the reason the Earth is in orbit around the Earth is the force towards the center of the Earth continually pulls the object toward the center of the Earth, but its forward motion carries it away from the Earth. And Newton was able to explain this using something called Newton's cannonball. If I, say, had a very tall mountain on the Earth, and I shot a cannonball off, it would come and it would fall down. Let's put more gunpowder in. Next time it'll go a little bit further before it strikes. And I could continue to do this every time, making it go a little bit further, a little bit further. If I shot it with enough speed, though, as it goes around, it's falling towards the Earth, but its forward motion takes it around until it eventually comes back to where it was. So satellites don't fall out of the sky because they're moving fast, about 18,000 miles an hour in case of the space shuttle. So once you get them to the right speed, they're going to stay there indefinitely, or at least until the small amount of friction caused by the little bit of atmosphere up there slows it down. One of the useful features of Newton's laws is that we can now measure how an object moves in a distant orbit, and if you can do that, you can measure the mass of the object. So for example, we can get the mass of Jupiter from measuring the orbits of its satellites. Newton showed that if you start with his 4 laws and consider a small object in orbit around another object, you can derive all 3 of Kepler's laws exactly mathematically. It's not easy, so Newton invented differential calculus in order to solve this problem. And we note that Newton's laws are much more fundamental than Kepler's, so they provide an explanation for the shapes. If nature follows Newton's laws, the planets must travel in ellipses. And second, they allow for situations that can't be dealt with Kepler's laws. So let's look at a couple of these examples. Comets. Newton's contemporary Edmund Halley recognized that you could apply Newton's laws to the motion of comets, which were nothing like circles. Some comets travel in parabolas or hyperbolas, which are really foreign to Kepler's laws, but they're entirely predictable by Newton's laws. In fact, Halley predicted the 75-year return of the comet that bears his name. He actually died before it got here, but when it came, it justified both his work and Newton's work. The other thing that Newton's laws give you is perturbations. So if you look hard enough at the orbits of the planets, you'll find they're not exactly ellipses. For example, as Mars goes around by Jupiter, it actually kind of moves out a little bit and back in, kind of this bump as it goes past Jupiter. So there are gravitational forces between the planets as well as between the planet and the Sun. Those extra forces perturb the motion of the planets away from being a perfect ellipse. Newton's theory tells us exactly how to deal with this problem, while Kepler's laws don't deal with the situation at all. Kepler's laws deal with the problem of one or more small objects orbit around a larger one. But it's possible for 2 objects of comparable mass to orbit around each other, as we'll see in binary star systems. Newton's laws have no problem with this. Both objects are in elliptical orbit around an imaginary point in space called the center of mass. In fact, we can now use this principle to detect planets around distant stars that are too faint to be seen directly. So as the planet orbits the star moves in a small orbital motion which we can detect and determine there's a planet and how big the planet is. And finally, Any civilization that lives near the ocean can make the link between tides and the moon. The times of high tide vary in a similar way to the times that the moon transits the meridian. But until Newton's time, it wasn't realized that the connection between the moon and the tides was gravity. Newton's theory can explain the timing of the tides, why there are 2 tides a day, and account for the effects of the sun's pull as well as the moon's. This is a good example of a scientific theory that was developed for one purpose being successfully applied to another phenomena. To understand why there are 2 tides a day, one has to consider the balance between gravitational force of the moon and the centrifugal force on the water. These together produce bulges on both sides of the Earth. So as the Earth rotates under the bulges, a person standing on the shore experiences 2 tides each day. The sun also raises tides about 1/3 of the size of the lunar tides. They sometimes add to the moon's and sometimes neutralize it, depending on the time of the month. The sizes and timing of the times depend on where you are. But tides can easily reach 20 to 30 vertical feet in some places of the world. Now, Newton's theory of gravitation is not the last word on gravity. If you deal with very strong gravitational fields, Newton's laws start to become inaccurate and eventually illogical. And Einstein's general theory of relativity supersedes Newton's theory. The differences between Einstein and Newton's theories are immeasurably small for all normal situations, including almost everything we're going to meet in this astronomy course. Which is why we continue to learn Newton's theory. It's much simpler. But when we get very strong gravitational fields, such as near black holes, Einstein and Newton's theories diverge and Einstein's work better. Now, people, such as Stephen Hawking, are finding situations where even Einstein's theory is not working and are looking for something even better. I want to talk here a little bit about space exploration. I'll talk a little bit first about rockets. Rockets are an example of Newton's third law in action. You heat gas very hot so it shoots out of the back of the rocket, and the reaction causes the rocket to accelerate forward. The difference between a rocket and a jet engine is that a jet sucks air or oxygen to burn the fuel, but a rocket carries everything it needs to burn inside, including oxygen, if that is the fuel it needs to burn. Most of a rocket is made up of fuel in tanks. As the tanks empty, they are dead weight and they are typically discarded. In older rockets, the engines went too, leading to multi-stage rockets. So for example, this is a cross-section of the Apollo rocket. The first stage, you had the 2 parts of the fuel, which was liquid hydrogen and liquid oxygen. You put them together, they create water, very hot water, it shoots out, and the rocket goes up. Eventually, these fuel tanks are empty and they're just dead weight that you don't want to try to accelerate forward, so the rocket breaks at this point and the second stage takes off. So today, when we launch a satellite by a rocket, it goes upward to clear the atmosphere, but then we have to turn on the side and boost the satellite horizontally to a speed of at least 18,000 miles per hour. So straight up, then turn around and shoot the satellite horizontally into orbit. If it's got the right speed and direction, great. If not, the orbit is in the wrong shape. And typically, the acceleration phase of a rocket launch only lasts a couple of minutes. So, if I'm here and this was my launch pad, and I launched it in the wrong direction, it would come up and it would come down. This is an elliptical orbit with the Earth at the focal point, but most of the Earth is inside this ellipse. So this is, say if I wanted to launch a missile to land somewhere else, I would take an elliptical orbit like this. I launch it, and then it's probably about here, its rocket burns out, and it just free falls to wherever it's going to land. If it's going too fast, it goes way out and comes back, and it'll go into orbit. It's an elliptical orbit. Most satellites, though, you want a nice circular orbit around the Earth, so you have to get it just right. Now, many satellites, including the space station, travel within a few hundred miles of the Earth's surface, so they take about 90 minutes to make one orbit. Higher orbits take longer. Remember Kepler's laws. So, for example, the moon is 250,000 miles, and it takes a month to go in orbit around the Earth. An orbit of 22,000 miles above the Earth's surface has a period of 24 hours. So if you put a satellite above the equator at that altitude flying east at the right speed, it appears to hover above the same point continuously. These satellites are called geostationary satellites. They're the ones that we use for communication, like Dish Network or DirecTV. Since your satellite dish does not have to move. So they're in orbit around the Earth, but the Earth turns the same time that it does, and so it always seems to appear stationary above the Earth. Now, to escape the gravity of the Earth, say we wanted to go to the moon or the planets, for example, you need to travel above 25,000 miles per hour. If you launch with a velocity less than that, you will always fall back to Earth or stay in orbit. By comparison, the minimum speed needed to go into orbit is 18,000 miles an hour. There is a mathematical relationship that explains the velocity that an object has to have to escape the gravity of a planet. You don't need to know this, but I just want to know the form. So the escape velocity is square root of 2, this is Newton's gravitational constant, so the mass of the planet divided by the size of the planet, or the radius of the planet. So the more mass, the harder it is to get away, or the faster your escape velocity has to be. So we've done this a few times, deep space travel. Man went to the moon between 1969 and 1972. Spacecraft have landed on Mars and Venus. They have also orbited Jupiter, Saturn, and one asteroid. And spacecraft have flown close to all the planets except for Pluto. Now, if I want to get to another planet, I just don't point a rocket at the planet and shoot. What we have to do is put ourselves in an elliptical transfer orbit and then cruise there without power in an elliptical path. So, for example, as the Earth is going around the Sun and Mars is going around the Sun, if I want to get to Mars, what I do is I take an object above the Earth and I shoot it and I put it into an elliptical orbit around the Sun. And I do it at just the right time so that as the time it takes the object to get there, so Mars might be here, and as they come, the two objects will collide, and you want then them to arrive there at the same time. That's when they talk about a right window or a launch window, when we can launch from the Earth and get to Mars, because Mars has to be in the right position so that those two will come together. Now, there are two reasons to go into space to study astronomy. Number one, you can study the planets close up if we send a spacecraft up there close. But we can also just put telescopes into orbit around the Earth in order to avoid the Earth's atmosphere. This is important because ultraviolet, X-rays, and other wavelengths of light don't penetrate the Earth's surface. So this concludes Lecture 3.